So let me tell you what I propose to do today and also in the next week. This is the beginning of the next week. You see, I should mention in the beginning that the whole thing is motivated by our need to understand properties of materials, and in most cases what we are concentrating on is quantum mechanics of material properties, especially because this is my view of focus of this lecture series, is that eventually we'll try to connect to nanomaterials, materials of great interest today. Nanomaterials, as you know, are of dimension of nano size, that is 10 to the minus 9 meter. So at such small sizes, many of our well understood dogma, they break down. For instance, normally we say that there's something called thermodynamic limit, that you go to the limit of an infinite system, and the meaning of that is that the number of atoms, the surface of the material, is much smaller compared to the number of atoms in the bulk. You can easily argue about it. Suppose you think of a spherical material, then the number on the surface will scale like the radius to the power squared, whereas the volume, the number inside the bulk will scale like r to the power cubed, and therefore as r becomes large, the surface to volume ratio goes like 1 over r, and therefore that goes to 0. All these things break down when you come to nanosystems. There's no translational invariance. So new science is required, right? I mean, for instance, the science of thermodynamics, science of electrodynamics, these are all macroscopic sciences, and we have to then think anew. Elasticity. Elasticity, in elasticity you define stress, strain, etc. And in terms of derivatives of displacements, but what is the meaning of derivative when you come to such small systems? You have to go to the atomic level, atomic structure, and it's like going backwards from differential equations to difference equations. I mean, Newton, Leibniz discovered differential equations as limits of difference equations. So now we're going the other way. So new exciting science is coming about, and quantum mechanics is very important because ultimately your goal is to make devices, your goal is to make quantum computing possible, and so properties of coherence is very important, which is a property of a quantum wave function. All these things will come up as we go along. And so the reason again also quantum mechanics is important is that suppose, for instance, you talk about the Drude behavior of electrical conductivity, then if you have a wire and then the electrons move in the wire, and it's a large wire, so it suffers a large number of collisions, which means that the dimension of the system is much, much larger normally than what is called the mean free path, that is the average distance that the electrons take to collide with each other. Much larger than the mean free path. That breaks down when you come to nanomicroscopic systems. There, the system size is comparable to the mean free path. Now, what is the meaning of mean free path? As the electron collides, it suffers a random change in direction, so its quantum phase gets decohered, right? And so for nanomicroscopic systems, you are able to preserve this coherence because the electron will not suffer collisions as it traverses the dimension of the system of interest. So it is that focus that we want to bring in. And for that, as other speakers have also emphasized, that what we are looking at are basically the electronic properties. Okay, that's why to deal with the electrons, you have to deal with the many-body problem, the Schrodinger equation of a many-electron system. So you need approximation schemes. Some of these things are being discussed by Professor Sushanta D. And you already see that even a two-electron system can become a little messy. And so when you go to multi-electron systems, you need approximation schemes, etc. Professor D. Sharma talked about real materials, their properties, and what my aim is to actually give you simple concepts, simple ideas which connect these very complicated material properties and to give you just very, very simple pictures. So in this endeavor, we saw that in a simple-minded model, which, as Professor D. Sharma emphasized, has great applicability, especially to transition metal oxides and other systems, is what is called the tight binding model, where the assumption is that, see, normally the electron wave function is all spread over. The electron is everywhere, like conduction electrons, for instance, in good metallic systems. But in many cases, what happens is either due to defects or due to other phenomena, you can actually say, well, the electronic wave functions are more or less localized at the lattice sides, though the wave function can spread over, so there is overlap, there is tunneling, there is this transfer matrix, various names are given to these things, and we will use the notation T for the purpose of our lectures, because D.D. Sharma introduced this parameter called T, which is called the hopping or tunneling matrix element. So, so tight binding model is a very interesting model, and now it's a way of also looking at the real space of the system. It's important to look at the real space now, because as I said, for coming to realistic nanomaterials, translational invariance is not there. So if translational invariance is not there, the block theorem goes out of the window, and therefore it's not very profitable to look at things in the momentum space. So looking at momentum space presupposes that the system has translational invariance. So you try to therefore now look at actually the real space, where the atoms are. This is the question that Feynman raised, that you go and you make a bottom-up approach. You go to the bottom, start from 1 atom, 2 atoms, 3 atoms, and then start building up your macroscopic system, and you go there from the real space. And the tight binding model is a very important model in that regard, where, as I said, wave function is more or less localized, and you still have possibilities of overlap. Maybe over nearest neighbors, that is the most important hopping process, but you may have also next nearest neighbor and further neighbor hoppings, as Professor D.D. Sharma pointed out. So, today we will also again look at the tight binding model, and what I want to do is something that probably physicists have worried about a lot, but today in the area of nanomaterials, there's no difference between physics, chemistry, material science, and so it's something like which is that what happens in the tight binding situation when you have an external magnetic field. You see, the electric and magnetic fields are two very important external fields that you can have, you can create in the laboratory, which influence the electronic properties. Because of course the electron, if you're subjected to an electric field, it will have a Coulomb force. If you apply a magnetic field, if you bring in spin, D.D. Sharma, when he was talking about magnetic properties, he was keeping in mind only the spin. If you have spin, then you have Zeeman interaction, and spins give rise to ferromagnetism, paramagnetism. What was not talked about by Professor D.D. Sharma is another important attribute of an electron in the presence of a magnetic field is because of its orbital motion. The electron is a charge, and you apply a magnetic field, you have this Lorentz force. So it is that aspect that we want to focus on, and that is where the Aharonov-Bohm effect comes in. So what is the Aharonov-Bohm effect? I'm sure, this is something that is not normally dealt with in any course in quantum mechanics. You won't find it in too many textbooks also. One book in which you have some discussion is a book by Sakurai. But I will base my discussion on a very wonderful, little small monograph. I don't know if IISc or Kolkata Library has it. It's a book by Tonomura. Is it strong one on there?
No, it's not there, but it's not available.
I think the title is something like electron waves. Electron waves are a wave. And Aharonov and Baum is an effect which is almost 60 years old now. Aharonov was a young graduate student, went from Tel Aviv to work with David Baum in the UK. And this effect is in 1959, there's a physical review paper, which the title of the roughly says that you have electron wave effects even though the electrons do not see magnetic fields. Okay? So electron wave phenomenon even when electrons do not see the magnetic field. This is very counterintuitive, right? Even the great Richard Feynman actually didn't believe this in the beginning. But then it took him 24 hours of thinking, and then he sent a congratulatory message, a telegram to Aharonov and Baum. So what is the AB effect? So I'll abbreviate it as AB. So what is ABE? So we already have seen that if you have a free electron, what is a free electron? A free electron has a kinetic energy which is simply p squared over 2m. I use m as mass of the electron. And this is actually an operator, right? Because this is like h bar squared over 2m del squared, right? This is an operator. It operates as a wave function. So, you know, you've been seeing this h psi, z psi is a stationary state Schrödinger equation. So you have to operate by this operator on psi. Okay, so P is like a del operator, right? Like you all see this. So what happens if you have a free electron? I have nothing but kinetic energy, and therefore you plug it in, and the solution says that psi as a function of, let's say, the vector x goes like e to the I p dot x over h x, right? Right? I will say this, right? Because if you do del square, you take the derivative twice, you bring down two p's, p dot p, and that will give you p squared. Note that on the left hand side, when you have operate by the Hamiltonian, you have this p is a quantum operator. Sometimes you'd like to indicate that by putting a hat or something like that. But this p is the eigenvalue of that Hamiltonian in the momentum space, right? And x is a coordinate. So e to the I p dot x is basically a wave, right, which propagates in the direction of p, and it has a wavelength given by the magnitude, like 2 pi over lambda, given by p then becomes h bar k, and k is 2 pi over lambda. And as we discussed yesterday, right, so this is an amplitude also, and normally this is what is called a quantum phase. This is not normally observable because the physical quantity that you associate with the wave function is mod squared, is the probability density of finding the electron at the position x, and the mod squared will wipe out the quantum phase. You will not normally see. It's a genius of Aharonov and Baum said that if you combine quantum mechanics now with electrodynamics, you will see a very fascinating effect. And this is what now we'll discuss. So what happens when you have a magnetic field on? We discussed yesterday that when you have a magnetic field on, you must change your canonical momentum by this factor, it's P minus EA over C, right? Where A is the vector potential, which is such that the curl of A will give you the magnetic field. This is also a vector. This is B field. And for the sake of definiteness, we'll assume that the B field is along the z-axis. So this is your z-axis, and we'll choose right-handed coordinate system, but this is x-axis, this is y-axis, right? Please. Right? So far so good? Okay? Right? So P must be changed, P must be altered by that quantity. So therefore, the quantum phase phi now phi of x now goes over to the new phi, which will be like e to the I over h bar P minus EA over C dot x. So you have a new phase factor, which is given by A dot x, the vector potential dot x, right? So what is the meaning of the vector potential? We can discuss this yesterday, that there is something called gauge invariance, gauge transformation. It says that I can add to this A grad of another scalar, and I get the same B because there's an identity says that curl of a grad is always equal to 0. So this is what is called gauge invariance. When you do quantum field theory, high energy physics, I mean it's all there. When you everybody will take it as though it's well understood. There's something called gauge invariance. And so now you can choose to work in what is called a symmetric gauge. Where A is a vector, it's a three-dimensional vector, because I've taken the B field along the z-axis and curl of A will give you B, moment's reflection will tell you that A cannot have any z component. Curl, the vector product is always normal, right, to that direction. So therefore, there's no z component. And you can easily work it out. Simple vector algebra, x times b. And so this is the symmetric gauge. Minus half yb, half xb, minus, so the notation is that this is the x component of the vector potential A, which is minus half yb. The y component is half xb, the z component is 0. To simply work out high school, what is curl of A, you'll find that it's the b times the k unit vector, which is along the z-axis, right? Okay. Now, the gauge transformation means that I can also equivalently go into an A by let's say if you choose your scalar potential to be like half b x y, okay, then you calculate grad chi. The grad chi will be a vector along the x-axis of magnitude half by, y-axis of magnitude half bx, half by, half by will cancel here. So then you get this times xb times 0, and this is called the Landau gauge. And you can also check that divergence of A is equal to 0 in all these cases.